All right, so today's video is topic 4.5, radioactivity. And so there's kind of two big ideas and that will be covered in this topic. So why are some things radioactive and some are not? So that ties into isotopes, and that isotopes can be one of two things, stable or unstable. You saw that a little bit in the PhET simulation that you played around with. And then how can we show this decay and what do atoms become to become stable? So a few things we need to clear up is some of the vocabulary. The issue is some of this is seen in everyday life, and so we need to clarify what we mean from a chemistry perspective. So radioactivity is the result of an unstable ratio of protons to neutrons in the nucleus. Obviously, the name nuclear chemistry is the study of just the nucleus. This has nothing to do with electrons. And so there's what's called the band of stability, that there's a specific ratio elements want to be happy. It's kind of like Goldilocks and the Three Bears, and they want to be just right. So typically elements up to atomic number 20 or calcium traditionally want a 1-to-1 ratio, 1 proton to 1 neutron. Above that, as you get into larger nuclei, you typically want about 1.5 neutrons to 1 proton is usually the ratio in order to get, again, a stable nucleus. So radioactivity is the actual process of happening because, again, that ratio is not correct. So a radioisotope is an isotope that is an unstable nucleus, and it's because of that ratio not being proper, and so it will go through decay on its own, and it can emit radiation. And so radiation is what's actually released from the nucleus. So here I have kind of an example. So you start out with your radioisotope here. So we usually call that the parent isotope. For some reason it's radioactive, depending on the ratio. When it goes through radioactive decay, it ends in a new nuclei. We call that a daughter isotope. And the radiation is what is actually released and what we detect. And so there's three main types. We're going to get into some of the more detailed types as well. But there's alpha decay, beta decay, and gamma decay. These two here are particles. This one here is a ray or a form of radiation energy. And so again, that's just clarifying some of the vocabulary. So nuclear reactions are not the same as chemical changes. So the idea is, if you think about alchemists, you've probably heard about alchemy or alchemists, and their goal was to change lead into gold. And at that time, there really was not much known about the atom when they were attempting to do this. And so they didn't understand that there was nothing they could do chemically to change cheap, abundant lead into rare, valuable gold. And so there's nothing you can do to change one element into an element of another chemically. So for example, if you burn something like methane, in order to burn something, you need oxygen, and you produce carbon dioxide and water. So in all the start and end, you end up with the same elements. Nothing new is produced in terms of identity, but you can make new compounds or new elements in how they're rearranged. However, what you can do is take two elements. Now here it's using deuterium and tritium. Those are just specific isotopic names given to hydrogen because there's one proton. So if you can combine those in a correct temperature, pressure, and alignment, they can combine together to produce a new nucleus, giving it a new identity, in the case of this being helium. So again, a chemical reaction that we see typically in day-to-day stuff is involving the electrons. Nuclear reactions have to deal with protons and neutrons. And the one thing that can be useful for us humans is there's a tremendous amount of energy released at the same time with nuclear reactions. So within the range of nuclear reactions, we have two types. And so the first thing, another vocab term here, is transmutation. So you probably think of mutation when you think of biology and mutating DNA. It's changing of it. And so that's the same thing kind of applied in chemical terms. So a transmutation is when the nucleus changes from one element into the nucleus of another, giving it a new identity. And the goal here is that an atom that is a radioisotope or radioactive is trying to change that proton-neutron ratio in a certain way to become something stable. So natural transmutations are one type that we're going to talk about. These happen completely natural on their own. They're not induced by humans. And so this typically happens with elements with an atomic number greater than 83. That's where you start to get into those larger nuclei. And so that's where we tend to have a lot more of our radioactive isotopes. So here's some examples of natural decay that can happen, or natural particles that can be released along with an energy form. Here is you can have alpha, beta, positron, or gamma. So how you can recognize natural transmutation is that you have one element to start. In this case, we have a nucleus of uranium spontaneously breaking down into thorium, and this is an alpha particle. So you always can recognize natural really easily by only having one isotope to start. The next type is artificial. And artificial is kind of like a game of pool that I think of, that you have to introduce a particle. Usually it's by bombardment. And so it's different from what you saw on the slide with natural, that we as humans can come along, hit the nucleus with something. A lot of times, in this case, this is a neutron that we can hit this atom with, and that causes a change to take place. So this is artificial. And so again, a way you can recognize this is that you have two things to start the nuclear reaction. And again, something has to come along to basically start it. So I kind of think of it like when you are playing a game of pool and you start the game by breaking. And so you have the white pool ball that you're sending towards your remaining, and it's kind of then breaks up the nucleus, so to speak. So artificial, like I said, typically there's, in not all cases, but when we take a look at like nuclear reactors here on Earth that we are using, that is using artificial transmutation to cause those reactions to happen. So you can bombard the nucleus, or there's two other types. And again, some of these do happen naturally. So we have fission and fusion. Fission is where you split large nuclei apart. So if you see an atom going from something of a higher mass into something of a lower mass, that's an example of fission. So right now, that's the type of nuclear reactors we have here on Earth, is that we usually use uranium as our fuel source, and that goes through decay, and we can kind of control that decay to produce however much energy we want. And so again, that's fission. Fusion, if you think of to fuse something, means to combine together. That's what the sun is doing currently, and that's where we take two nuclei of smaller mass and combine them to produce something of a larger sort. So these aren't on your notes or anything like that, but this is just two diagrams to, again, explain what we have going on. So fission, usually you have a target nucleus like uranium in a uranium reactor. We can hit that nucleus with a neutron. That changes the arrangement. We then get neutrons that are then released, and we have these daughter isotopes, or the product of making something lighter. So like I said, in a uranium reactor, we usually use uranium-235. When we hit it with that neutron, we can then have that nucleus rearrange. It produces two byproducts. We produce krypton and barium. More neutrons are released. That's useful because then you can have them hit other uranium nuclei and continue that process. And that's where nuclear reactors can become dangerous, is if you aren't controlling this, it gets to be a runaway reaction like they saw in Chernobyl back in the 80s. So fusion, this is what's taking place in the sun. We have deuterium and tritium, both of which are just, again, fancy names for two isotopes of hydrogen. Because they have the correct conditions, you need a high temperature and pressure. That's why these reactions tend to happen in stars, and we aren't able to accomplish these in our nuclear reactors because we can't get the temperature and pressure needed to maintain it. So we fuse those together. We produce something of a higher mass, the helium, lots of energy being released, just like we saw in fission, and then there's a neutron as a byproduct as well. So this is a table that gives you the properties of the four main particles and rays that we're going to talk about with natural transmutation. So one way that a nucleus can become stable is by releasing an alpha particle. An alpha particle is going to be released from a nucleus that is very, very heavy, and it needs to get rid of some of that heaviness or mass. And so it can kick out two protons and two neutrons from the nucleus, and we detect it as a helium nuclei being released from the nucleus because, again, it has a mass of 4 and it has 2 protons. We can also use the Greek letter alpha to represent it, and because it's 2 protons, 2 neutrons, the mass is 4, and the charge is +2 because it's just 2 protons. No electrons are coming out of the nucleus, just 2 protons, 2 neutrons. These, because they're kind of a heavier mass particle when it comes to radiation, how can we protect ourselves? This one, your skin is able to stop these, or a sheet of paper. Now, if you ingest something that has something that's radioactive that emits alpha decay, that's a little bit different. So overall, in terms of issues with radiation, these are very minimal compared to others. So beta is interesting. So this is an electron that comes from the nucleus, and you're probably thinking, where's an electron coming from? It's the nucleus. There aren't electrons there. We'll talk about that here in a moment on why that's there. But what we detected as is having a mass of 0 because there is an electron. Electrons really essentially don't have mass. There's 2 ways we can write it. We can show the beta symbol, or we can write it in our nuclear format, showing that the electron has no mass, E for electron, and the charge here. So that gives us a -1 charge. Because it's a smaller mass, it's going to have a little bit more energy. So you need something like aluminum foil to block it. Positron is another thing where we're starting to get into some interesting physics here, and mechanics on the structure of the atom. And so basically it's the antiparticle of an electron, no mass, but it has a positive charge. And that's, again, we'll get into that here in a second with how it's breaking down. It has a charge of +1. It's still an electron essentially, so aluminum foil will stop it. And so this is a little bit higher power that it has a little bit more concern. Gamma rays are the ones we really have to look out for. The reason why is these 3 are particles. This one is a ray or energy, no different than electromagnetic energy like visible light or X-rays. And so because it's a wave or energy, it starts to get to be more dangerous and harder to deal with. So its mass, it doesn't have mass, and because it's energy, it again, isn't going to have mass, and it doesn't have a charge. So we show it as the Greek letter gamma with a mass of 0 and no charge. And so it takes several centimeters of thick lead, or it can take meters of concrete to stop these because, again, it's a wave. When you go to the dentist and they put that really heavy apron on you, it's to protect you from those high energy X-rays, which can be problematic as well. So by putting lead in that apron, that is protecting you from that X-ray emission. And so these are the more dangerous ones to deal with. So what we're going to do with the rest of the notes is practice and look at what do nuclei become in order to become stable. So the first type we're going to look at is alpha emission. So alpha is represented here. And so we use that nucleus of 4 to He, because what happens is we start out with this heavy nucleus of radium-226 and its atomic number is 88. It releases, so this arrow is showing us after the arrow, this is what's being released, and we have 2 byproducts. So it's trying to bring down its mass, so it kicks out 2 protons and 2 neutrons, so its mass is 4 and atomic number is technically 2. So what is left in that nucleus is the mass has gone down by 4, so take 226 minus the 4, the new isotope is going to have a mass of 222. Subtract your atomic number by 2, and that gives you a new atomic number of 86. So this becomes a new element because we have a new number of protons, and this becomes radon. So again, it's released this, and the mass and atomic number go down, again in the hopes to bring that ratio closer together to make it stable. So what we're going to do is practice with 2 equations with alpha decay. So from here, if you don't have your periodic table, you definitely are going to need that. So here we have polonium, and the thing that I can recognize that it's alpha is this helium nucleus being released. So we're going to figure out what is the new isotope produced from this decay. So it emitted a mass of 4, so that means your mass will always go down by 4. So the new mass number here is going to be 214. Of that mass of 4, 2 protons were released with it, so our new mass number becomes 82. We can then determine the identity of it using this atomic number, never your mass number. So the atomic number 82 tells us that the element is lead. One way you can check is these two, and these two should add up to conserve. So it should match the original mass number and the original atomic number to show that protons and neutrons were conserved. So in example B, we're just working backwards to figure out what was the original isotope that produced an alpha particle in this francium-221. So we add our mass number of 4 to our mass number of 221. That tells us the original mass of the radioisotope was 225. Adding these two together, that tells us that the original atomic number before it lost 2 protons was 89. Element 89 is actinium, or AC. Again, you can add these to compare to make sure mass is conserved. So that is alpha decay. The next option is beta decay. And beta decay is weird because what we detect is an electron. And like I said, electrons are not found in the nucleus. So this is what happens when an element has too many neutrons and it needs to bring its neutron number down. That's what's demonstrated here. So what happens is a neutron has the capabilities to decay, and it decays and breaks down into 3 things. It has a proton, and what happens is that proton remains within the nucleus. So a neutron transitions into a proton. Another byproduct of that is an electron. That is going to leave the nucleus. That is what we are able to detect. And then this is called a neutrino. And I'm going to leave that for if you go on to maybe AP chemistry. I don't know if physics would really get into it at this point. If you go on to college, you'll definitely get to hear about neutrinos. But the big idea is the electron is what we detect, and it's because a neutron became a proton, an electron. And that's going to explain what we have going on here. So we have carbon-14 releases a beta particle, and if you notice, the mass stayed the same because, again, a neutron and proton have the same mass. So that's why mass number doesn't change. But this neutron became a proton. Therefore, what happens here is your atomic number goes up because you created a proton. So that's where it gets a little bit goofy. So here we have thorium-228 releasing a beta particle. Again, this neutron just broke down into a proton. So the mass stays the same. That neutron became a proton. So our atomic number therefore goes up by 1. It becomes 91. And when we check it out on the periodic table, we can identify that as protactinium, or Pa. Going back to what originally started here to release this beta particle and plutonium-226, or 236, excuse me, is the mass stayed the same. Again, a neutron had to break down to make this proton, so therefore our original atomic number must go down by 1 because we haven't made that proton yet. Atomic number 93 is Np, or neptunium. The next idea is positron. This is another odd one that's very similar to beta decay, except we release an electron that has a positive charge. So this is the example here with the beta plus decay, or positron. So you can see here we have 4 protons, 3 neutrons. The decay takes place. Well, our neutrons went up by 1 and our protons went down. So this is the opposite of what happened. So this is an example where it has too many protons and it needs to get rid of protons and bring up its neutrons. So again, like I said, it's all about a balance act between those 2 types. And then we get a positively charged electron released. Notice here, mass stayed the same because, again, the mass of the nucleus didn't change. The atomic number went down because we lost a proton and gained a neutron. So in this case, we are going to subtract our atomic number. So here we see that it's a positive charge. That's how you recognize that it's positron and not beta decay. So mass is going to stay the same here. So we have a new mass of 15. And what happened here again is a proton broke down into a neutron. So our new atomic number is 7 because we lost one of those protons, and that is nitrogen. Working backwards, mass was staying the same here. Again, we haven't broken down that proton just yet in the original starting, so that means we had one more proton to start, and this is TH, or thorium. Moving on, gamma. I'm not going to fill in any examples with gamma because the thing is, this one's really easy. A gamma ray, and we can add this on here if you want to add this to the example, has no mass, no charge, because it's energy, not a particle. So this just helps de-excite an electron. So barium-137 starts out, it emits this ray, it gets rid of some of this energy that's in the nucleus. And in doing so, it didn't release any particles. So the mass doesn't change, the atomic number doesn't change, therefore the identity doesn't change. So if you see that it's the same on each side, you can assume that we are talking about gamma. So the last segment for today is the artificial transmutation. Again, when you look at all of these examples on the first part of this backside of your notes, the one thing you'll notice is in all of the examples, they start with one radioisotope, oxygen here, thorium here, barium here. And then it breaks down into subsequent particles. These are artificial. You'll see that we start with two things, that you have to collide a nucleus with something else, and we can produce products, sometimes one product, sometimes two. So we're going to figure out what is this X, what needs to fill this in. And the one thing that will help us is that the mass needs to be conserved and the atomic number or protons need to be conserved. We can't create or destroy those protons, they can convert though. So we can see here that to start, we have an atomic or mass number of 40, and we end with a mass number of 41. So that means this original particle has to have a mass of 1. Notice that our protons are conserved with the protons on the start side. So that means the protons here are 0. So this is not an element off the periodic table because there's no element with the atomic number 0. So what this tells me is this is a subatomic particle. It has no protons, but it has a mass of 1. What subatomic particle has a mass of 1 that isn't a proton? Your only option is a neutron. So this is a neutron that hits calcium to produce this potassium-40, and it releases essentially a proton or a hydrogen nucleus. So in this next one, we have molybdenum, atomic number 96, hit by a hydrogen atom. So the conserved mass here is 98. So here I have a mass of 1. So 98 minus 1 tells me my other mass number must be 97 to conserve. I can see that there's 43 protons to start and 0 here. So that means all of them had to go into this product. So all 43 protons. That's going to tell me what was the new nucleus formed here, which is technetium, or TC. This one here is kind of a goofy one in that it's called electron capture. So another thing nuclei can do is come along and take in a nucleus, or take in an electron into its nucleus and work it through that way, basically doing the reverse positron or beta decay. So if you take a look, the original mass is 37 and 0. So that means our mass number here is going to stay the same. In electron capture, what happens is that you take an electron, combines with a proton to produce a neutron. So that means it combined with one of these 18 protons. So think about what happens here. The mass stays the same. Our atomic number is going to go down because, again, an electron and proton combine together to make that neutron. So we subtract 1 from here, and our new atomic number is 17. That means this is chlorine. Last one here, if we combine these together, 239 plus 4 gives me 243. 94 and 2 gives me 96. I can see that one part of the mass is conserved here from the neutron. So 243 minus 1 is going to give me a new mass number of 242. Here I have a total mass of 96, or not a mass, but 96 protons. no protons here, so all 96 ended up here. And this is curium or Cm. So if you have questions, if something felt confusing, if you want more examples with a certain type, please feel free to reach out to me. Your homework is going to go through and practice with all forms of transmutation.